Yes, and the final version it was, let me check. Yes, it was like this. Limit of x approaching 0, gx, which is going to be x ln minus x squared minus 2 or 2x. So it's our final version. And we are going to use the formulas of limits ln, which are ln a over b equals to ln a minus ln b, and ln a multiplied b, which is going to be ln a plus ln b. So let's apply this here. So it's going to be x will remain the same, and it's going to be just ln, sorry, it's going to be ln 2 minus x squared minus ln 2x, which is going to be, of course, limit x approaching 0. It's going to be limit x approaching 0. If you also apply this rule, second rule, it's going to be ln 2 minus x squared minus ln x minus ln 2. So this is our final formula. Let's erase this. So our final form was limit x approaching 0, x multiplied by ln 2 minus x squared minus ln x minus ln 2. So it's our final formula. And here we have to use L'Hopital rule. But we cannot do like this. So we are going to add a new variable. So it's going to be t. So we are going to add x equals to 1 over t in order to make it divided by t, and let us use L'Hopital rule. So in this situation, t equals also to 1 over x, and it's when x approaches 0, this condition. So t is going to be 1 over 0, which is infinity. So our limit will change, and it will be a limit t approach to infinity, and replace everything. So it will be ln t plus ln 2 minus 1 over t squared minus ln 2 divided by t. So here we can use L'Hopital rule. So we will take derivatives. So what's L'Hopital rule? This limit x approaching to a when fx and gx. So it's going to be limit x approaching to a f derivative x over g derivative x. So this is our L'Hopital rule. So let's erase this part. So our final version was, yeah, like this. Limit x approaching to infinity, I'm sorry, t approaching to infinity. So ln t plus ln 2 minus t squared, 2 minus 1 over t squared minus ln 2 derivative over t derivative. So it's going to be limit t approaching to infinity. Here it's going to be 1 over t plus, here it's going to be 1 over 2 minus 1 over t squared multiplied by 2 minus 1 over t squared derivative. It's by using the chain rule, and here it's going to be just 0. T derivative is also 1. So finally it's going to be limit t approaching to infinity, sorry, yes, t approaching to infinity, 1 over t plus, here if you count, so here it's going to be 0, so minus 1 multiplied by 1 over t squared, it's going to be 1 derivative multiplied by t squared, so it's going to be 0, minus, it's going to be 0, minus 1 multiplied by t squared derivative over t power of 4. So it's going to be 2t here, 2t minus, and also minus 1 multiplied over t power of 4. So it's going to be eliminated, and negative gives us positive. So it's going to be 2 over t cubic. So here is going to be 2 divided by 2 minus 1 over t squared multiplied by t cubic. So it's our final version. So let's erase everything. Okay, our final version was limit t approaching to infinity, 1 over t plus 2 over 2 minus 1 over t squared multiplied by t cubic. So here what we can do, actually t goes to infinity, and we see that everything is here is with numerator and denominator, so we can just eliminate them. So we can plug in infinity to this t. So it's going to be 1 over infinity plus 2 over 2 minus 1 over infinity squared multiplied by infinity cube. So if you count like this, is going 0, going 0, going 0, so totally the answer is going to be 0. So at the end what we got? We got that limit x approaching to a, like to a, fx is going to be e, and limit x approaching to a of gx is going to be 0. And we had the formula firstly, which says limit x approaching to a fx power of limit x approaching to a gx. So our limit x approaching to a fx is going to be e, and our limit x approaching to a gx is going to be 0. So it is 1. So we prove that limit x approaching to 0 cotangent x power of sine x is going to be 1.